All right. Hey guys. Uh, so I guess you could probably just go ahead and start. Some people might still be coming in because I noticed last time a couple people arrived around like 5:10, and after that. So I kind of want to try to wait to start the first problem, to start working on the first problem until then, um, on the off chance that a couple more people trickle in. But in the meantime, yeah, someone just joined. So in the meantime, if you have any questions, I'm happy to try to answer them.
Wait, yes, Professor, I actually have some problem.
Uh-huh.
Yeah, so in lecture 4.5, you actually explain the quotients of convergence sequence, right? And
Mm-hmm.
then when you're like inside, you said that by forcing the absolute value of Sn minus R, then the epsilon of M, epsilon times M times absolute value of S, we can get that. We can just like get that like the absolute value of 1 over Sn minus 1 over S is smaller than epsilon. So I'm just
Right,
wondering like
yeah.
how's the logic? Yeah.
Sorry, how does what?
Like how's the logic? How can we like where how do you know that's like epsilon times M times the absolute value of S? And
Right, yeah.
why is what yeah, so like why the absolute value of Sn minus S when this value is smaller than the epsilon times M times absolute value of S, we
Mm-hmm.
can deduct that like
Right,
the
right, right.
absolute value of 1 over Sn minus this is yeah.
Yeah, sure. Okay, I'll try to go through that very carefully. So,
Uh-huh.
right, so in this case, Sn converges to S, which is not equal to 0, and um, all the Sn are not equal to 0 too, right?
Yeah.
Uh,
Yeah.
so we took, just for context here, right? This is the
Mm-hmm.
infimum of all these absolute values. Well, they like to use a colon in the book, which is greater than 0, right?
Mm-hmm.
So we know this is greater than 0 from like a previous thing we did, right?
Yeah.
Uh,
Yeah.
so what we're doing is now we take capital N such that um, Sn minus S is less than this given epsilon
Mm-hmm.
times M times capital, or times absolute value of S, right? Okay, so now the question you're, if I understand correctly, you're asking is just why does this make, so why does this ensure that 1 over Sn minus 1 over S is less than epsilon, right?
Yes.
Okay, well, the reason
Yeah.
is that, so 1 over Sn minus 1 over S is the same thing. If you just combine these fractions, right, you get Sn minus S over Sn S, right?
Yeah.
Because, so the expression inside is just Sn minus S over Sn times S, right? If you
Yeah.
just combine the fractions. So I'm gonna erase this. So basically, now, because of the way we chose all the stuff that we did, we know that, here, let me change color real quick. Yeah, we know that this part is less than epsilon S, right? We know that
Yeah.
this part is greater than M, or greater than or equal to M, right? So
Uh-huh.
the overall expression, right? So if you make the numerator smaller, or if you make the numerator bigger, right, then you make the overall value bigger. And if you make the denominator smaller, you also make the overall value
Yeah.
bigger. So by replacing this top thing with this expression, I make the numerator bigger, right? So this overall, oops, I forgot to change back here. So this overall expression here is still less than epsilon ms over ms, right? Which is just epsilon, because
Yeah.
by taking this thing and replacing it with epsilon ms, I increase the value. And by taking this and replacing it with m, I decrease the value down here, which also increases the overall value, right?
Okay.
And then these things just like cancel out. Does that make sense?
Yeah, yeah.
Yeah.
But
So
like, where can we get the absolute value of Sn minus S is smaller than epsilon times m times absolute value of S in the first place?
right. Well, that's because we chose capital N to make that be true, right? Because basically, right,
Uh-huh.
once we're given epsilon, and then we define this little
Yeah.
m like this, and then also like S is just given to us too, right? I mean, we don't really have
Yeah.
control over any of these things, but these are all, right, in this expression here, these are all just like positive numbers, basically, right?
Yeah.
So this whole thing is just some positive number, right? So, and then, so this whole step is we can do this because Sn converges to S, okay?
Yeah.
So the point is that we assumed that Sn converges to S, and what that allows us to do is basically we can take any number we want, and then we can like pick capital N to make this number be smaller than the number that we want to make it smaller than.
Okay.
Yeah. So
Yeah,
we just
okay.
like chose this number here, epsilon times m times absolute value of S. That's just like our sort of clever choice for a number to make this be smaller than, because then later it makes things work out for us, basically.
Oh, okay,
Right.
okay. Okay, I got it now. Thank you.
Yeah. Mm-hmm. Good question. Any other questions? Yeah, so the material, oh, sorry, go ahead.
Yes, I have a question, thanks. In the book, when they state the definition for convergence, they like make some comments and it says, in view of the Archimedean property, the number n in the definition can be taken to be a positive integer. I'm just confused about what they're talking about.
Yeah, it's just like a really sort of a technical thing, which is just the fact that like, okay, so like, let me think how to explain this. Basically, if you define convergence by saying like Sn, oh, dang it. So Sn converges to S if whoops, let's say, so for all epsilon, there exists an n, which is just any number. So let's say this is a real number, such that you know, Sn minus S is less than epsilon for all n greater than n, right? Then you can basically like, this is the same as defining in, let's say, even just natural numbers. Because, and basically it's like, because if any n exists making, let's call this like star is this condition here, right? Then like star is also true for the smallest, or for actually for any integer bigger than n. Okay, so let me explain this. So basically, like capital N is supposed to be kind of like the cutoff in the sequence, where like after that point, the sequence is like close to the limit, right? So the idea is that it's like if you can find a cutoff that's like any real number at all, right? Little n is just like an integer. Little n is only ever allowed to be an integer, right? Because that's like the index of the sequence. So if you're saying like this statement is true for all integers little n bigger than this like random real number, then this statement will still be true for all integers little n bigger than like any integer that's bigger than this number, right? So like let's say I took n to be like, yeah, like 3.8, right? Then I could take n equals 4 too. It's like the same thing, doesn't matter. So it's just like sometimes it's convenient to use the definition to say that there exists an integer capital N, but also sometimes you want to be able to let capital N be like any random number, basically.
Got it. Thank you.
Yep. Mm-hmm.
But when solving problems, should we use the case where it's for n is a real number or n is an integer?
Well, it just depends on the context. So basically, like
For sure. Mm-hmm.
if you're trying to prove a sequence converges, then like it doesn't matter. You can make n be literally whatever you want. Like it can be an integer or it can be a real number. It's like, you know, it's up to you really.
Gotcha.
But if you're like trying to, so that's when you're trying to prove something converges. But if you like know something converges already and you're trying to like invoke that somehow, then like sometimes it is useful to invoke it in a way to be like, because when you invoke it, right, what you're saying is like, okay, we can find a capital N, right? Because it converges, we know there exists a capital N such that blah, blah, blah is true, right?
Mm-hmm.
And so the only reason that technical thing is in there is to let you say, not only that we know a capital N exists for which this is true, but that an integer capital N exists for which this is true, just because sometimes that's like a convenient thing to be able to do.
I see. All right.
So it's like if you need capital N to be an integer, then like make it be an integer. Otherwise, you know, don't worry about it.
Mm-hmm. For sure. Thank you.
Mm-hmm. Any other questions? Okay. So I have several problems about sequences and like adding sequences and like divergent, you know, sequences that diverge to plus or minus infinity and stuff. So the first one that's like somewhat simple, but it's kind of like a warm up. I'll call it a warm up. Is this problem. So let's see. What can we say about the convergence of Sn plus Tn if Sn and Tn converge? Sn converge, yeah, or like, yeah, let's say one converges and the other doesn't, and both diverge. So yeah, so pretty short one. I think maybe just you guys can take a couple minutes to just think about it on your own. And we can resume at like 5:25. All right, so let's just go over this. So let's see. So the first one hopefully was just instant, you know, that was kind of a gimme because we proved in lecture that this means Sn plus Tn converges, right? Now, how about this one? Would anyone like to venture an answer?
I think it doesn't converge.
Yeah. So
Because
why do you say that?
I was thinking an example like 1 plus infinity is still infinity.
Yeah.
So
So
if
yeah,
there's no
that's
upper bound for one,
mhm.
and then like there's no upper bound for overall.
Yeah, exactly. So like, yeah, that's a good intuition, I would say, which is that like basically if you take a convergent sequence, right, as you go further and further out, it sort of just becomes almost just like a constant, right? It just becomes like a number, basically. It like gets really, really close to a number. That's the whole idea of what it means to converge, right? So if you have this other divergent sequence, which could be doing anything, I mean, it could be going to infinity, or it could be like oscillating, jumping around randomly, right? If you just like add a constant value to all of those things, that's not gonna like make the divergent behavior go away, right? It's just going to like shift it around somewhere. There's actually a very fast kind of argument to prove this. So the answer is that Sn plus Tn diverges, right? Because otherwise, like here's the argument actually. If Sn plus Tn converged, it's like sort of a contradiction thing. Then Sn plus Tn, right? That would make Sn plus Tn a convergent sequence. And then you could subtract, like, let's say that Sn converged and Tn diverged. So let's say Sn converges, Tn diverges. But then, oops, if Sn plus Tn converged, you could subtract Sn. And that would have to converge it. That would have to converge. Because both of these two would be convergent, and that would mean that Tn actually has to converge too, which we're saying that it doesn't, right? So does that make sense? I kind of stumbled over some words there, but yeah, so hopefully that makes sense. This is actually just like, this is a perfectly rigorous argument that shows that if you add one convergent sequence and one divergent sequence, the result has to be divergent. Okay. So I'm going to erase it. And then the last one, what can we say if both of them diverge? Rahul?
I said you wouldn't know because they could either go both towards infinity or they could be like oscillating and phase cancel and then it would converge.
Sure, yeah. So no info. Yep, perfect. Yeah, really easy examples of like adding two divergent sequences and getting a convergent sequence is literally just like canceling out a random like like you could say like, you know, Sn equals like, you know, literally anything like -1 to the n, and like Tn is like -1 to the n, aka -1 to the n plus 1. Right? Then you just add them together and you get 0. So yeah. That's that. Just a nice little warm up. So this kind of gives you hopefully like a taste of how things are gonna develop, because it's gonna, as we introduce like more and more properties of sequences, we'll get like more and more sophisticated problems about just like basically asking, you know, do there exist sequences with like certain combinations of properties basically. And some of those will become kind of like, you know, like there's just like a lot of different, you know, like combinations that you can like examine, I guess. So yeah, it's fun stuff. Okay, so now I'll give you like kind of a more substantial problem, and I'll let you guys work on them together. Yeah. Actually, I could just like figure everything. So here's the next problem here. So yeah, this is actually from the textbook. So show that if Sn diverges to infinity and the infimum of Tn, so Tn is another sequence, right? Note that there's no absolute values here. It's just the infimum of the values of Tn is greater than negative infinity. So meaning basically, this is literally just another way of saying that Tn is bounded below. Then Sn plus Tn diverges to positive infinity. Okay, so I'm gonna put you guys in groups now. Da, da, da. Yeah, all right. Okay. So yeah, we'll take yeah, let's resume at 5:40. All right, so let's see. Let's take a look at this. So, right, I'll start the proof off. So let's, I don't know, just for convenience, let's call this assumption 1. Oh, good. And let's call this assumption 2, right? So let's say we assume 1 and 2. Now, what should be the next line of the proof? Anyone want to guess? Yeah, Rahul.
Let m be a real number.
Yeah, very good. Very good. Right.
Would you get
Remember,
like partial
Uh-huh.
credit for just saying that in a proof?
like maybe, you know,
Okay.
epsilon's worth partial credit.
An epsilon of partial credit.
Yeah. Sorry, I wish I could be more generous, but I appreciate that. Yeah, I appreciate the spirit. So yeah, right. Remember, like whenever you're trying to show something about like, you know, convergence or divergence to infinity or whatever, you kind of have to like let these variables exist, which you have no control over, and then you have to like do stuff with them, right? So that's kind of the general pattern that we want to follow. So okay, now our goal, right, is to find n such that Sn is bigger, or sorry, not Sn, Sn plus Tn is bigger than m for n bigger than n, right? That's what we want to do. So m is like this bar that we have to like get over, right? Okay. So the key ingredients are, right? I mean, so the thing that will basically, you know, hopefully this is kind of also becoming a pattern that you become familiar with, right? But the idea is that there's one assumption that's kind of like helping us, right? Sn going to infinity, that's like what's helping us. That's what's helping this sequence go to infinity. And that's going to be the thing that we ultimately leverage to pick capital N, right? So that's like our good, you know, helpful assumption. And then there's kind of a confounding factor, right? Which is Tn. Like if we didn't know anything about Tn, then this would be impossible because Tn could be working against Sn and making the sequence like not go to infinity, basically, right? So the thing is that we have to like control Tn, like to prevent it from being too bad. And we have to leverage what we know about Tn, right? Which is the fact that it is bounded below, right? So let's call m the inf Tn. I'm just going to abbreviate it like this, okay? And so m is like some, you know, real number, right? Because this is bounded below. So then I'll sort of take, I'll sort of write out kind of what we want to do. So we want to take n such that blank is greater than blank for n greater than n. Okay, so what do you think should go in these blanks? Let's say blank number 1. What do you guys think? I'll fill in blank number 1. Maybe this is a little bit confusing. Sn, right, is the thing that we actually have control over. We can like leverage what we know about it, right? But what goes in blank number 2?
Is it m?
So not quite, right? Because we want Sn plus Tn to be greater than m, right? So let's kind of go back to the goal maybe. So we want Sn plus Tn to be greater than m, right? And that's kind of equivalent to saying we need Sn to be bigger than m minus Tn, right? Yeah. So right. And so yeah, how do I explain this? Right. So the thing is, you know, how can we make sure that Sn with one sort of constant, right? I mean, you can probably guess what it needs to be for just from looking at this, right? Because there's only so many like constants flying around. But basically the answer here is m minus little m because, right, because m is less than Tn for all n. So m minus little m is bigger than m minus, whoa, Tn. Okay, it got kind of cramped. But does that make sense to you guys? So, you know, you just have to think about like the worst case scenarios, right, are when Tn gets like really negative, basically. Okay. And it makes sense if you look at this expression that like if Tn is allowed to get really negative, then little m is going to be some like super negative number, like a big negative number, right? So this is going to be a very large number overall because we're subtracting this large negative value from it. And so that's going to force Sn to be really big to compensate, but that's exactly, you know, how it should be, right? So basically, we kind of look at the worst case scenario, like little m is basically like the worst case scenario of how negative Tn could be, right? And we just like shift Sn to make sure it always compensates for that, right? So maybe that, hopefully that's sort of an intuitive explanation here, but yeah, you can kind of like do a little bit of algebra to figure out, right, like what should go here, basically. That's kind of like the scratch work you have to do. That's a common thing too, is that like you find yourself doing these like doing scratch work to figure out what condition you actually want to impose on your like the sequence that you know something about, right? If you know a sequence converges, you want to figure out like what quote unquote epsilon to use, right, to make it be smaller than. So like for example, with the reciprocal sequence thing, we used like epsilon times little m times absolute value of s. That was the thing we came up with using our scratch work as like a bound to enforce on the absolute value of Sn minus s, because we knew that we could do that. We knew that Sn approached s, so we could pick whatever number we wanted. So we did some scratch work to figure out like a good number to pick. And it's just the same principle here. It's the same structure of the argument, right? So then, because we chose our capital N intelligently, right, so that this condition is true, then for all n, oops, for all n greater than n, we have Sn plus Tn, oops, boy, Tn, all right, whatever, is greater than Sn plus little m, which is greater than m minus little m plus little m, right? So this cancellation happens, which is what we expect, which is capital M, right? So are there any questions about that? It takes a bit of getting used to this whole sort of process of, you know, taking what you know and kind of seeing through the argument, like what you're going to, you know, where you're going to be picking your capital N, right? And how you want to pick the capital N, like what condition you want to use is based on like what else you know about the sort of the confounding factors up here. Yeah. Okay. So if there are no other questions about that, I do have one more question. This is a little bit of a tricky one. And yeah, maybe I'll give you guys like 5 minutes or so. It should be sort of short, but it is a little bit tricky. So just be cautious when you're thinking about this. So here's the question. So true or false? And I love true or false questions, by the way. You're going to see a lot more of them. If Sn approaches infinity and Tn is a sequence and Sn plus Tn does not approach infinity, right? So it does not diverge to infinity. That's what this means. Does Tn diverge to negative infinity. Okay, so I'll put you guys back in your groups just to discuss this a bit. All right, so hopefully, I think everyone should all be back now. Right, so I kind of maybe telegraphed the answer to this, at least as far as the true or false part goes, since I said it was tricky, right? It seems at first glance, this probably seems like something that should be true, but I'll just tell you right now that the answer is actually false, okay? So the answer is false. But what I'm curious about is if any of you guys have a counterexample. Would anyone like to describe a counterexample to this statement? So basically what we need is an example of one sequence that approaches to infinity, one sequence that just does something, and the sum of them needs not to not approach infinity. But the Tn sequence is not allowed to go to negative infinity. That's the other thing.
Our group came up with one possible candidate.
Sure.
And it's basically a sequence that's not bounded above nor below. So for example, the example you gave in class, -1 to the n times n for Tn.
Yeah. Yeah, that's actually exactly, so that I think that's the exact counterexample I had in mind. So you could have this sequence and then you could make Sn be like just n, for instance, right? So then Sn plus Tn would be like something like, so it would be 0 if n is odd and 2n if n is even, right? So it might take a second to understand fully why this is a counterexample, right? So let's go through everything. Okay, first, does Sn approach infinity? Let's see, I'm gonna, right? Yes, that's pretty clear, right? So now Tn is a sequence. Okay, that's fine. Now, does Sn plus Tn not approach infinity, right? So look at this sequence. This sequence does not approach infinity. So this does not approach infinity, right? It diverges. This sequence does diverge, and it also happens not to be bounded above, right? So diverges and it's not bounded above, but does not approach infinity, right? So that should maybe give you some respect for exactly how sort of delicate the condition of converging to infinity actually is. It's not like something that happens all the time. Some kind of special, you know, it's easy to violate the condition of converging to infinity. Okay, so right, that's true. And then also clearly Tn does not converge to, or not, does not diverge, sorry, does not diverge to negative infinity, right? Because it's going all over the place. So does anyone have any questions about this example here? Very good. Yeah, so, you know, I would suggest, like, if you want, you can tinker with this a lot and see like what you can get. So like, for example, what about instead of this, we say, hold on, let me like erase this stuff. What if we change the statement to be like, instead of this, we make it be like bounded or something, or like Sn plus Tn converges, or Sn plus Tn is, let's say, just, well, I don't know, Sn plus Tn, you know, is unbounded below. I mean, that's kind of similar to what we just did, or and so on. Like you can come up with whatever stuff you want, or you can mess with any part of this, right? You can change, well, especially the hypotheses, basically, you can mess with, and that's like a very healthy type of exercise to do. Yeah. So anyway, I'm gonna end this meeting, and I have office hours like right now, basically. So I'm gonna go start that one, and if you want, you can. You're free to like join that one too. So yeah.
Thank you.
Mhm.
Thank you so much.